Good evening. Welcome, everyone. It's great to see so many folks on such a beautiful evening. Thanks so much for coming. My name is Laura Hazler, and I am the Director of Programming for the Wisconsin Alumni Research Foundation, as well as the Director of Outreach for the Morgridge Institute for Research, and the Director of the Illuminating Discovery Hub for the Wisconsin Institute for Discovery. So I get to work with all three of the organizations in this building who collaborate to bring this Crossroads of Ideas series. The idea behind this series is to make this space that you're in, the town center, really a crossroads of ideas to promote conversation, dialogue, and spark mutual interest between people in the community and researchers doing groundbreaking work here on campus at UW-Madison. And what we try to do in this series is bring topics forward that are important to all of us in our lives, often more front page than necessarily science page, but that happen to be the subject of advancing research. And this semester, we are always delighted in the spring to feature a couple of projects that are the focus of UW-WRF 2020 awards to really push the boundaries of research that is high risk and high potential reward. And Professor Stanley's work is in that category, so we're excited to hear what she's doing with her 2020 work. Before I introduce tonight's speaker, I do want to mention the other events that we have scheduled yet this semester. We try and have these once a month on a Tuesday evening during the academic year, so we have two more yet this spring. In April, we will be featuring an event that we tried to have last month, but we're hit with snow. We had 2 consecutive snow cancellations for this series. I am trusting that on April 9th we'll be in the clear, but you never know. And we'll be talking with a number of some of the foremost authorities on the ethics and social implications of gene editing, human gene editing in particular, through the CRISPR technology. You may have heard of some work going on in China that came to the fore a few months ago. Most of the people involved in this session on April 9th have been consulted at a global level on the implications of this kind of work. So you won't want to miss that on April 9th. And then we'll be rounding out our semester on May 7th with a researcher, another 2020 investigator, who was featured not long ago in the New York Times for her groundbreaking work on the impact of fake news. Again, very topical, front page and science page. So that's what we're bringing you yet this semester, and then the series will come back in September. And if you're on our mailing list, you'll hear about it when that time comes. If you aren't and you'd like to be added, that's just outside these doors right over here to my left. So with that, I don't want to take any more of your time before introducing tonight's program. All of our sessions run about 40-45 minutes of lecture, and then we'll open it up for audience Q&A. We record all of these, so we ask you if you do have a question, raise your hand, wait for one of our mic runners to reach you, and that way we capture your question in the recording, and that helps everybody, because if you have the question, other people will be wondering about it as well. We're going to end promptly on the hour at 8, but Professor Stanley has agreed to stick around if folks want to ask a few more questions and you don't get that chance during the Q&A. So with that, I am delighted to welcome Emily Stanley, who is a professor in the Department of Integrative Biology and the Center for Limnology here at UW-Madison. She got her bachelor's in science degree from Yale University and her PhD from Arizona State. Her research group investigates biogeochemistry and ecosystem processes in rivers and lakes and how they are affected by human and physical drivers. She is the lead principal investigator of the North Temperate Lakes Long-Term Ecological Research Program and is also involved in National Science Foundation funded projects examining long-term and large-scale dynamics in lakes, stream metabolism, and novel approaches for detecting rapid ecological change. She is an author on over 120 peer-reviewed articles and has served on the editorial boards of the Journal of Geophysical Research, Marine and Freshwater Research, and Ecological Applications, and is a senior editor for Limnology and Oceanography Letters. She was named an Aldo Leopold Fellow in 2006, an Ecological Society of America Fellow, and a Society for Freshwater Science Fellow in 2018, and received, and I hope you'll explain Aslow's G.E. Hutchison Award in 2018 in recognition for her outstanding and synthetic contributions to our understanding of the roles of hydrology and the biogeochemistry of nitrogen and carbon in lake and stream ecology. We are very fortunate to have Emily Stanley on our campus and to be able to welcome her this evening. Please join me in welcoming.
All right, thanks very much for that introduction. I will explain what ASLO is in just a second. Yeah, so it's great to have this opportunity to talk a bit about this 2020 project that I've had. It's really been a lot of fun, and we have been able to do things that I did not think we would be able to do. But it'll tell you a little bit about the project and how it developed and where we're going with it. But before I dive into it, I want to say science is a team sport, and in this particular storyline today, these are some of the prominent players that have really helped in the project and helped move it forward, and you'll be seeing more about them as the talk goes on this evening. Okay, so what's ASLO? Let's just revert. The L in ASLO stands for Limnology, so it stands for the Association for, they just recently changed their name. It used to be the American Society of Limnology and Oceanography, and now it's the Association for the Science of Limnology and Oceanography. So imagine a lot of people in the room know what limnology is, but I want to make sure that everyone knows. So limnology is the study of inland water, so lakes and rivers and streams of all varieties, whether they are lovely and pristine like many of these ones up north, or a little bit less so like many of these in the southern part of the state. Streams are in there. And Wisconsin really is a fantastic place to be a limnologist. We are bounded by water on 3 of the 4 sides of the state. We have just a wealth of water, and it seems to me when I moved here 20 years ago, I really learned quickly that everybody in this state that I met has some connection to water. And so it's a great place to be. And of course, here on the Madison campus, we have Lake Mendota that a lot of people say, oh, Lake Mendota, this is the most studied lake in the world. Is it? Is that true? I prefer to say something that my colleague John Magnuson said, which is it's the best studied lake in the world. My office is right about there. It's fantastic. I have a lakefront view, so I feel very fortunate. Now, Wisconsin has a very special place for the study of limnology that tracks back to these very handsome gentlemen, Ed Burge and Chancey Juday. Burge in particular is largely credited with being sort of the father of North American limnology. At one time he was the chancellor here at UW, and he made a lot of the other professors work for him and build him pieces of equipment. It's good to be the boss, I guess. But these guys really started doing quite a bit of research, particularly in northern Wisconsin and the Northern Lakes District there, but also some sampling of Lake Mendota, and really began to get some of the data sets together and begin to get an initial idea of what that lake was like. And they really laid the foundation for some of our earliest data we use in our research. And from these gentlemen, the legacy of studying limnology continued. The next was Art Hazler. This is the man who our lab is now dedicated to. He's the person who actually, you all owe perhaps a debt of gratitude in building the Center for Limnology, the lab on the lakeshore. He stopped the plan for a parking lot that would have been basically where the terrace is today, so very important. And then my colleagues, when I got here, went from Art Hazler to John Magnuson, Jim Kitchell, and Steve Carpenter. So we have this tradition of ongoing research, and many, many other people outside, beyond the Center for Limnology, who have been engaged in the study of Lake Mendota and on. And it's really, these are just a few of the heroes of limnology in Wisconsin. So we have this early start to studying limnology. I like this. There are no ties in this room, but there is a tie right there, sampling on the lake. And these gentlemen started, as I said, sampling in Lake Mendota, and we continue this tradition through this LTER project that Laura mentioned in the introduction, of sampling in many of the same ways, not all the same ways, but many of the same ways that Burge and Juday studied. Here is Ted Beer collecting zooplankton in the middle of the lake. And so we have this record, or this history, where these guys would go out to the deep hole here to do this routine sampling, and we continue this on today. So this has been fantastic, and this is part of the reason why Mendota is the best studied lake. We have these data sets that are really unusual, right? We have this long-term ice record that has been a topic of discussion because it's been declining. We have shorter and shorter ice duration. We've lost about 20 days of ice cover over the last century on average. We can see other things. These are Daphnia. These are the grazers of Lake Mendota, the little crustaceans that like to eat algae and try to keep the lakes looking a little bit less than pea green. This guy, the fat one on the left, the Daphnia pulicaria, is the one we particularly care about, and we can look at how its populations have ebbed and flowed over the decades. So these are the sorts of things that really form critical raw material for research. Now, generating these data sets is hard work. You go out, lots and lots of detailed measurements. This example is temperature, but we collect a whole suite of physical, chemical, and biological variables very carefully, very fastidiously. We take care of the data. It's publicly available. So this is a nice picture of Ted doing this. It's a lovely sunny day. Not every day is a good day on Lake Mendota, of course, so sometimes it's really not very pleasant to go out. And this is where some of the new technologies to do limnological research become really valuable and really important and have been inspiration for some of the work that we've been doing. So, limnologists, lakes are generally smaller than oceans. We don't have the same access to resources all the time that oceanographers have, but we take some cues from them. And one of the cues that we have taken from the oceanographers is using buoys. Okay, so this is scaled to the sides of the ocean here. They're not all this big, but apparently this one is. Here's our version, a humble version. This is an early generation of taking advantage of these opportunities to start using buoys to do research, to be able to sample in the lake on those days that are really not particularly pleasant. This is David Buoy, the Lake Mendota's buoy. And we have there's a phone app for it if you want to find out what the weather conditions are in the middle of the lake. But what you see up here, floating on the top, their weather station and so forth, is really just, the literal tip of the iceberg, because beneath, hanging down from David, are a set of environmental sensors. And this is just sort of some examples of these that measure things like pH and temperature and dissolved oxygen and so forth. And David is at work all the time once he goes out in the spring until we take him back out in the fall, and he's a snowbird, he winters in Stoughton. And the great thing about these buoys, is we've learned very quickly, is we can see things with tremendous detail that we just can't do if we go out manually and ride boats out to go do these things. So here's just a very straightforward example of temperature in Lake Mendota going from right around where we are right now, where the lake is the same temperature top to bottom. It's mixing because all the water is the same temperature. And we start seeing it warming up and doing this characteristic stratification where you get warm top waters that have low density sitting on top of cooler, higher density waters to form this sort of two-level layer cake until it cools, until it mixes again in the fall. We really get these tremendous details of how this process of stratification develops, persists, and then goes away in the fall. That we just couldn't get because we just couldn't go out all the time. And one of the examples, too, of the things of having these buoys out there and being able to see things that we normally can't see, you can see in this example here from a couple of falls ago, where we had this hot spell, and for a few weeks we actually got a double layer cake. So we had the normal cool temperatures in the bottom, and then we got this stratification on top of the stratification that persisted. So we have this sort of micro-stratification. And being able to see these is possible because, again, the buoy is there at all times, taking a whole bunch of measurements for us. This has been really important. This has been a very big step forward for limnology to be able to have these sorts of technologies to get these high-frequency measurements And in fact, there's a whole group called the Global Lake Ecological Observatory Network that is developed that takes advantage of using buoys and the data that they have. So this is good, but there's a little problem, right? So here we are. The question is, what are we missing? Because we have just this buoy right here. And I like this picture. This is showing the land use in Madison and the surrounding areas. We see farmlands, we see dense urban lands, more suburban areas, and the lakes are a blank, just a blank. And yet, we know they're not a blank. We know they're not homogeneous all over the lake surface. This is a picture of the lake coming in that one of my postdocs took as she was landing in Madison, and you can see an unfortunately familiar site there of an algal bloom developing. So we can see these things, and we know perhaps if the buoy is here, we will not measure this that's happening over in that part of the lake. There are other things I bet many of you have seen if you've gone out to lakes and rivers in addition to algal blooms. You can see plumes of sediment come in. This is from James Madison Park from the Clean Lakes I stole from their webpage there. Another Northwoods favorite is dissolved organic matter. Okay, so there's this brown material coming off of a very wetland-rich watershed flowing into Lake Michigan here, excuse me. And it is this nice brown color. So this is sort of like a concentrated cup of tea, if you like, draining out of the landscape and going into the lake. And it's this very rich brown color. And all these cases, this organic material, these sediments, and the phytoplankton, this green color from the algae, we can see all these things because all of these molecules either scatter or absorb light, and that's great. Unfortunately, there's a huge number of limnological variables that do not scatter or absorb light, and we cannot see them. Now, if you can see something, a satellite can also see them, so these sorts of variables have been studied in great detail through remote sensing techniques. And this is a new technology that is really exploding as well, the very big advances in terms of what we can see from satellites. But they can only, again, see these three things because of their light absorbing or scattering properties. So here's an example, right? Does everyone recognize this? Yeah. Yep, there we have, this is the lovely Lake Erie, featuring one of its very epic algal blooms here. And really easy to see that. It was so big, even you didn't have to drink the water to know it was happening. And here is a satellite picture that's being generated from the folks at NOAA, and you can really see that they can, I will say these are slightly different dates, but you can really see the development very nicely. You can see differences in the intensity of this. This is fantastic, and we really are, there's leaps and bounds of advancement going on where we can see the spatial distribution of these algal blooms and where they are and maybe how they develop, assuming it's a nice clear day and they can get the picture. Now, Lake Erie is diminutive by the standards of Great Lakes, but by comparison to Lake Mendota, it's pretty big. So satellites do not have a big problem seeing it, but when we start getting into these littler lakes, you can see that what they're sensing here is one or two color shades. They start not being able to pick up any of the spatial variation in smaller and smaller lakes, and a lot of times those small lakes don't even show up at all. So this is a good advance, but it has some important constraints in terms of the size of the lake, the weather, and also the variables that you can see across the lake surface. Now, the other thing too is, again, we've just seen the algae here. It would be really nice if we could couple these with other variables like the nutrients, for example, or some aspects of the water chemistry that gave us a clue about the conditions that help shape these algal blooms. So, not surprising, following these epic blooms that happened in Lake Erie just a few years ago, they actually deployed buoys. They did not have any buoys on the lake. So they wanted to be able to figure out the sort of limnological characteristics that accompany these big events. And they put them here in this end because this is really where the problem area is, this western basin. And they have a whole bunch of these monitoring buoys that they can really get a much better handle on the conditions that are in the lake at the time these blue-green bacteria break out. But if you look closely in this particular example here, some of them are right on a bloom, some of them are away from the bloom, so they are seeing little bits and pieces of it. Okay, so we still, even though they have this suite of very sophisticated tools that they have deployed, we still have a little bit of problem filling in the blanks in these cases here. And the other part of the problem is 10 buoys, a buoy. All right, I have a question for you. How much do you think a buoy costs? I guess the answer is it depends on how big it is and what you're doing. We figured to build, deploy, and take care of a buoy probably costs about $90,000 to get it up and running. So that's quite a bit of money. You can't just scatter these things willy-nilly. You have to be very careful and thoughtful about them, and then also in terms of what you measure from the buoys. So really what we want is both of these things. We are greedy, right? We want information on the spatial distribution of things, and we want lots of information about different variables so we can understand the conditions and the causes and the consequences of these algal blooms. I mean, effectively, what we really want to do is take this buoy and have it be everywhere, right? So this is the topic of what we did during our 2020 project, was to try to figure out how we could get the buoy to be everywhere effectively. And this really, I would say, is mostly the initial work to get this going was due to my two grad students, is Luke Loken on my side and John Crawford on the other side, who came up with this idea of the FLAME. So the Fast Limnology Automated Measurement Platform. And I think everything needs a good acronym, and they came up with a good acronym. Not saying the terrorist was involved. But the basic idea here is take the buoy, okay, take your sensors that measure the things you want to measure, and bring the water to the sensors, and then drive the sensors around. That's all it is, okay? So it's really like putting the buoy in the boat and driving really fast. Okay, so this was just the basic idea here, and there is a reason this box is orange here, because here's one of the prototypes. It's good. It started humbly. We are limnologists. These guys have great technical skills, but they have some limits. Yeah, so you can see this is sort of a scruffy looking thing, and I will say in their defense, this boat was made particularly small so they could take it in streams to be very mobile. But this is one of the first generation versions of this device where you have the sensors and you can go take it in different parts of the lakes and measure things. All right, so they came up with this idea and they started building and working on things. I would go down to our basement where our boat slip is and where our workshop is and see what these guys were up to and check out what they were doing in the lake and offer them my wise advice. And you know, a lot of times I'd go and this is what I'd see. I'd see boxes open and people fixing things, trips. I paid a lot of bills for Ace Hardware. Yeah, tools and wiring. We can see we went from the orange box to a larger black box working in the workshop. This is Paul Schramm, another one of my graduate students. These guys are really good. I mean, Paul actually took a lot of engineering classes. They were extremely good at building things and doing things, but they did this iteratively. Try to, did it work? Does it not work? If it didn't work, then it fell into the bottom of Lake Mendota and we tried something else. We thought we were on to something here, but you know, there were limits in terms of what it was, and we ran into some problems with some sensors heating up and things like that. And I think we got to this point where we realized we could really, you know, when you get yourself into trouble, you really need some professional help. So we got some professional help. And this is where we formed a collaboration with these engineers at Physical Sciences Lab. This is in Stoughton, which is near where David spends his winters. But so these engineers normally do things like work with physicists and build neutrino detectors. They sort of made their claim to fame in building the IceCube neutrino detector in Antarctica. This is some pretty high-profile things. So I'm incredibly grateful to these guys that when Luke and I showed up in their parking lot, they were very kind and solicitous. I could just imagine what they were thinking as they're going, oh my God, what is this mess here? But you know, they're peering carefully and very interested, and they then had stepped in and we collaborated on improving the structure of this device that we had built and making putting the pieces together a bit better. And this is, you can tell they're a little bit more professional. This was the mock drawing that we actually used for our UW 2020 proposal to show this looks a little bit different than all those photos I showed you guys of shots of the workshop floor and things like that. The most disappointed of all is we did not get the boat. But this was the concept drawing. You can see a little bit more sophisticated. This is Barb Biratella, who was became the lead engineer for this project, really talented young engineer. And this is her delivering the super flame, or that's what we're calling it, that looks a little bit neater and tidier than what we had come up with. And there's Paul Schramm. And then this is Kevin Gauthier, who is one of the undergraduates who's been really involved in this project as well. And you can see, genuinely happy to see this box delivered to us because we knew, we could go out and give this thing a run. All right, so inside, besides a bunch of conduit and piping and pumps and things like that, we have put a large number of environmental sensors that we have bought. These are mostly commercially available devices, and there's not going to be a test. I'm not going to ask you what all these things are, but the point is, there are a whole bunch of different things that we have been able to plumb into the flame to measure in these lakes that really vary from the standard of temperature and pH to some very sophisticated things having to do with stable isotopes and things that are measuring metabolic activity of E. coli, which is interesting health problem that we all want to avoid in lakes. And so when we are sort of going full flame, we can measure 16 different variables. And these things will collect data at a rate of, sub-second, and there's a lot going on. They don't just measure pH, they'll measure a whole bunch of other supporting data with it. And so another key part of this project was that we were able to rope Mark Gaylor in here, who is really good at programming. And Mark was able to develop basically some software that marshaled all these data streams together and helped us keep track of it. This is this part up here, where you can see there's this real-time display of what the sensors are telling us in the lake. And here's another one of the part of this where it gives information on the location in the lake, and so you can drive the boat and actually see where you are as you go. This one helps us if there's a problem with one of the sensors, or if we run across something that we think, that's really interesting, let's go back and have another look. So this was a critical step forward as well in being able to do that and have that real-time feedback on the device. All right, so here we go. This is the parts. This is all the parts put together here. This is the intake and exhaust and also a gas exchanger, so we can measure carbon dioxide and methane. This is the new super flame, and here it is going into the flambeau. This is operation. You can see we did not, like I said, get that spiffy speedboat, but we hold out hope. All right, so these are the parts. Now, how does it work? Okay, so, got ahead of myself there. So there's a boat that has the flame in it, and what we do is we go to a lake and do this sort of grid pattern back and forth with these sensors going, and they're all measuring bunches of things and responding. You can see in this particular example, one side of the lake has a slightly different concentration of the representative variable relative to the other one. And we do those things, and then we can take these thousands of data points that we get and use some interpolation techniques and develop a map like this. So now we can see the lake. All right, so as we were working on this, like I said, we thought we had something. We thought it was interesting. And I think to me, really, it's like, oh man, this is awesome, is the example of trout bog. Okay, this is a very, other than having great data associated with it, this is one of our long-term study lakes. It's fairly unremarkable. It's a dark stained brown lake. It's about 2.5 acres in northern Wisconsin. It's a lovely place to be on a clear fall day, but it's nothing special about it. And this is one of the earliest places that John and Luke took the flame to go do some mapping, and this is what they found. Just all sorts of variability in these things. Nothing was uniformly distributed across the lake at all. You can see we have a lot of patterns where we see edge effects associated with the middle of the lake versus the shores. We also have some directional changes here. You can see that we later figured out was associated with groundwater flows into the lake and things like that. So this was great. This is for me very much of a moment of an aha moment, thinking, man, these graduate students are awesome. All right, so clearly, lakes are no longer these homogeneous, well-mixed reactors that they are often described in models and things like that. So now we have this opportunity to explore and figure out more about what spatial variability is like within lakes. And this is another great part of Wisconsin. There are lots of lakes to choose from. So both Luke for his PhD and Paul for his master's did some surveys of lakes, about 40 lakes across the Northern Highlands, to really get a handle on to figure out, was trout bog weird, or was there more to it? Was this a normal feature of lakes, to see all this sort of variability? So here's the short version of what they found after driving this boat back and forth in grid patterns all summer long for a couple of summers. Is, first of all, if you look at the same variable across a whole bunch of different lakes, you can find very different spatial patterns, sometimes really pronounced patterns, sometimes not. So these are 3 maps of how far down into the lake light penetrates. Very important. It sort of sets the limits on how much primary production you can have in a lake, how much algae can grow. So we have Little St. Germain, where we have lots of variability here. Here in Mendota, we have a gradient from one side of the lake to the other. And then this is Diamond Lake, which Paul, he studied this for his master's, called the world's most boring lake, because there is just no variability at all. And it's okay to go sample in the middle of this lake, and you're fine. But now we know that. All right, so we can look at one lake, and we can look at a whole bunch of different variables. So this is like the trout bog example, and you can see all the different sort of modeled colors tells you we have these spatial variability here and all these sorts of different variables. Temperature, dissolved methane, conductivity, which is a measure of sort of how many dissolved ions you have in the water. Chlorophyll for the algae. This is oxygen, and this is blue-green bacteria, the pigment that is characteristic of blue-green bacteria there. So lots of variability within the lake for all sorts of variables. Some are more variable than others. Very complicated to talk about variability in variables, so bear with me. And of course, adding to this, we also have change over time. Okay, so this is carbon dioxide and methane dissolved in the water of Lake Mendota. And sometimes it's pretty boring and uniform across the lake, and other times it's tremendously variable. Depends on the time of year and what's going on with the lake. So, spatial variability is the rule rather than the exception. And this opens up new and fascinating doors of what are the questions to be asked next. And this is some of the things that, again, Luke and Paul, it sounds like I'm talking about the Bible, but I'm talking about limnology. I won't talk about John and Mark. But these are just some of the basic questions that these guys were exploring with their research. What parts of the lake chemistry or biology are most variable? Why do they vary? What creates it? What do we need? What can we learn from the spatial data about processes in these ecosystems? And really, what are some of the uses to find out from these maps? I'm just going to give you, because I could talk about this all night, but Laura will come and tackle me. I'm just going to give you a rapid sampler of some of these questions and answers that these guys have done for their research. Okay, so what attributes are the most variable? It tends to be basically variables that are susceptible to biological processes. Methane is the winner. It is the most variable of all the things that we measured. Although turbidity, so this is sediment particles suspended in the water column along with phytoplankton, is also quite variable, but really it's the biologically affected variables that tend to be very patchy and heterogeneous in lakes. So I should say, yeah. So what creates this variability from lake to lake? Well, this one's complicated, but there's sort of three different things that you can recognize depending on the lake and the variable. One is sort of where are they in the landscape, or how are they connected to the drainage? So you have some lakes that are high in the landscape, high out, on top of a hill. This is Wisconsin after all, it's not that high up. Isolated lakes tend to be more homogeneous, but as you go downstream to ones that are connected to streams or have streams flowing in and out of them, they get more variable and more variable. The shape of the lake itself is important. Round lakes tend to be less variable, as you might imagine, than these ones where you have lots of bays or islands or things like that, where you have more contact between the water and the sediments, where a lot of these biological processes are happening. And then if the lake is very, very productive, like Lake Mendota, we tend to see more variability because there the organisms are really affecting the chemistry and the biology of a lot of the variables in the lake. All right, so what are some of the consequences of this variability? And again, I'm going to use an example that has been of long-standing interest to me because I'm very interested in carbon cycling. And this is some work that Luke has done where he compared what we would think is going on in the lake based on the buoy versus the flame. And so he went out, and Paul went out and helped him once a week from the time the ice went out until till December to do this mapping. And here, what this shows here for methane is the range and average values of methane. So you can see sometimes of the year, what you see from the buoy in the red is very similar to what you would guess, or excuse me, what you would arrive at from the mapping. But there are other times where we have enormous amounts of variability across the lake, and the buoy is not a very good way to know what's going on in terms of how much methane there is in the lake. And this really amplifies in the fall, and this is associated with the lake cooling down and mixing and turning over. And this is a time of the year when a lot of methane comes up from the bottom of the lake up to the surface and then eventually into the atmosphere. So in fact, if you can look at another way of looking at this is you can imagine 1,000 different points across Lake Mendota, and if you wanted to know how much methane was leaving Lake Mendota and going into the atmosphere, you pick any one of those 1,000 points, you could have that total that you would guess for the summer of how much methane is leaving would be anywhere from over 400 millimoles leaving to down here to less than 100, depending on what point you'd picked. And here is the buoy. It was low, as low, as low. This is the whole lake average. It caught up at the very end because of the mixing and the big, basically, delivery of methane from the bottom of the lake. But if the buoy had been over here, it would have been really, really low and really have underestimated how much methane Lake Mendota was delivering to the atmosphere. So this really tells us where we sample or how much we sample becomes really important for lots of variables. All right, so another question that Luke was interested in, and this is a collaboration with the U.S. Geological Society survey, was sort of what can this tell us about what lakes and rivers are doing, the processes underlying the patterns that we're observing. And one that is also very near and dear to my heart is nitrogen cycling. Here in the Midwest, we are unfortunately very good at putting nitrogen into circulation and sending it downstream to the Gulf of Mexico, where it creates a eutrophication problem there. So there's a lot of interest in trying to figure out how not to send that nitrogen downstream. And we have a lot of good answers to this, but these guys were interested in really focusing on the main channel itself and seeing where we might be holding on to some of this nitrate, and these might be places to pay particular attention to from a management perspective. So they had a Huck Finn moment here. started in the Twin Cities and basically took the flame down the Mississippi River to St. Louis to map out all sorts of water chemistry along the way. It was very much of an epic journey for these guys. And here you can see on the far side is a trace of the nitrate. This is the form that the nitrogen travels downstream in. As they went along the way, and they sort of had these points where they would pay particularly close attention and do more detailed mapping within pools above locks and dams. And here's the answer for where the river holds on to its nitrate and prevents it from going downstream. Lake Pepin. That's it. This was the only place that they found any sort of removal of nitrate. The rest of the upper Mississippi River is basically just delivering nitrate downstream. It's a bit of a bummer. So here's Lake Pepin. The flow is here. It comes in, nitrate comes in very high, and by the time it leaves the lake, it's actually very low. You can see this longitudinal profile, the nitrate decreasing, decreasing, decreasing. And we also, in this trip, had a sensor to measure nitrous oxide. So this gives us a clue that the process of the process that is depleting the nitrate. It's a microbial process called denitrification that is a great process because it actually takes that nitrate and it puts it back into the atmosphere where it belongs. All the rest of these pools, all the rest of the river is basically just sending everything downstream, and we see a huge jump in the concentration of nitrate as we hit the Iowa and Des Moines rivers in Iowa, in particular. It just never goes down after that. All right, so there are many fantastically interesting questions that we have begun to nibble at with the flame that are, frankly, pretty academic. Understanding spatial variability and patterns and controls of it. But I think there's a lot of things here which we are beginning to explore too, which is there are a lot of good uses for this information as well. And I think really clearly we are mapping water quality in real time for things that we usually have to wait a while to find out. So some examples here, this is conductivity. So this is the amount of ions in the water in University Bay. This is where the university puts a great humongous pile of snow. So this is runoff of that snow melting and the salt that comes off of parking lots and things like this. Another example here, this is a specialty device that was brought to us by a collaborator from Austria to measure activity associated with coliform bacteria. So we can take the flame out and find places where we're getting signatures of potential coliform activity. Rather than grabbing a sample and waiting a week, this will tell us some places to watch out for after rains, up in Upper Yahara, and then some hot spots here in Mendota and further down as well. So this is this one is a very new and in development sensor that is not commercially available yet. And then an ongoing project that we've just started this last year is, can we use information within the spatial patterns to give us a warning that an algal bloom is on its way, so we can maybe do something about it, or at least warn people that it's on that a big bloom is coming? And so, we're not doing this in Lake Mendota. We're doing this in northern Wisconsin lakes. But you can really see here how blooms in Mendota have this very characteristic development in one part of the lake, and then very quickly they're sort of flop over into this very green state. It would be certainly nice to know that this is coming before it happens. All right, so that is the rapid tour of the flame. This is in here to remind me to pause to begin to wrap it up here. So we have been through this 2020 project, spending a lot of time really perfecting the technology of being able to do this, and now opening the door to using it to ask scientific questions, and whether both, as I said, academic or applied. And this is where we are right now, and it is exciting. It really is pretty exciting for us because we are really getting some traction on being able to do these things. And I think we're just really at the beginning of this process. So my sort of aspiration is the next time we see maps that we don't see the Yahara chain of lakes as blobs, that we might get some detail on what they look like spatially from lake to lake and within lakes. and really very excited about the opportunity to keep using this to ask more questions about processes and patterns within lakes. So thank you. So questions, I guess? Yeah. Oh, yeah, microphone, right.
I have a question about the lake levels. They're getting so high lately. Doesn't that really increase the algae blooms?
Yeah, so the lake levels can. I think the thing that really is driving the algae blooms is things like the manure that people put on their fields, and that'll be, especially when the ground is frozen and that find their way into the lake. I think we may be in for an interesting summer this year because, of course, we had frozen ground, we had manure on it, and then we had that massive melting that put a lot of that enriched water into the lake. So it could be another exciting summer for that.
We increase the water flow through the lakes.
Well, it should. The only problem with that is that there are a series of pinch points, and this is a good where you just can't move the water through the lakes all that quickly. I mean, the way water gets from Mendota into Monona is through that very, very narrow creek, and there's just you can't rush it, unfortunately. And there are a few others further downstream as well. But in fact, you're right though. If you do flush the water through there, it does improve. The water quality does improve. Yep. Stoughton. It's all about Stoughton tonight.
Yeah, I was wondering, wouldn't it be possible to devise an unmanned boat that could be controlled electronically from remote points?
Yes, and in fact, that exists. So they have these gliders in the ocean, and it's really cool. They take advantage of some of the buoyancy differences, and they can go up, dive up and down, up and down. And then there's a device called the Eco Mapper that you can have as your very own if you have somewhere in the range of $85,000 to $120,000. That you program it with GPS points, and it will go. But the problem with the Eco Mapper is that you can only put, at the moment, a few sensors in there. There are advantages to having a boat where you can just clutter up all sorts of things. But yes, I mean, the one thing the Flame does not do is it doesn't go very deep, because you can't go fast with a metal rod hanging out the back of the boat. It'll just, and I know that. PVC snaps even faster. Yeah.
Yes, what is it about Lake Pepin that allows it to convert nitrates more readily?
Yeah, so the secret to Lake Pepin is that it slows the residence time of the water in the lake is longer than any of the other lock and dams. I mean, that's all right. So Lake Pepin is natural, and its residence water just slows down much more and stays in there longer, so there's the time to have stuff happen. And in the other ones, I mean, in the other pools, you can see nitrogen going away in the backwaters, things like that. But those backwaters it's a small amount of water, and it's not really attached to the main gush of water that is charging down the middle of the channel, the river channel.
I have a couple of questions. One is, do you have to often calibrate the sensors? The second question is, you mentioned about Lake Pepin. Is it possible, by understanding the mechanism, we could create a mechanical, like a small plant, which will mimic Lake Pepin, and then you can build a series of such plants, and then finally the water discharged will hardly carry any nitrogen.
So the first question about having to calibrate the sensors, the answer is absolutely yes. And so usually that's sort of there's a ritual each day when these guys go out to do the mapping. It starts with calibrating sensors. And then, of course, the great thing about Mark's display is you can see as you're driving if something is going terribly wrong with the sensor. So if there's a problem, you can stop, or you can take it offline and say, let's get everything else. We'll fix the sensor later. So yes. Now for Lake Pepin, so there have been many discussions about how best to get the nitrate out of the Mississippi River main stem. There was a calculation that's been done about if we built a big dam to hold the water back, how big would it have to be? And I think the answer, correct me if I'm wrong here, Brent, it's about the size of the state of Louisiana. So not very practical. And then the other solution is to have a bunch of very small flow-through wetlands to have many of them stack up. That takes many acres and effort. I mean, that's thousands of projects, and there does not seem to be the will or the finances or the opportunity to have lots and lots of little projects where you launder the water through sort of these wetlands, unfortunately. I mean, the Mississippi River is a working river. There are a lot of, there's traffic that goes up and down it. I think the bottom line is once the nitrogen gets into the main stem of the Mississippi River, it's too late. We need to stop it before it gets there. That's the trick. Oh, hold on, we'll get you and then we'll go back to you.
Hi, thanks for your talk tonight. Can you tell us what's the future of these sensor arrays? Meaning you have a mobile platform and there's still at least one buoy out there.
Yep.
And so will there be more buoys deployed because there are things they can do that the mobile platform can't? Or will there be more mobile platforms? What does the future look like?
Yeah, good question. So buoys are awesome. And what we have been moving toward are smaller buoys that measure fewer things that are distributed in different places in the lake. And Mark has been involved in that as well. Mark is here, by the way. There he goes. So, and we've even been putting, the particularly new thing we've been doing with the buoys is putting them in fall and having them spend winter under the ice. And that has been another eye-opener as to what goes on there. So that goes on. We have some of our northern study lakes. We've got buoys on those. Big buoys with lots of things are expensive, and so that's a constraint. So we will always have a core set of buoys, and then maybe complemented by satellite buoys. And then the flame, there is more interest in using it than we have flames to send around. So we will keep using it as much as we can, for sure. As I said, we've got a project in the north that the flame will be working very hard on that this summer, and we may try to see if we can get something running in the south to keep an eye on the algal blooms. We'll see, yeah. Oh, yeah.
Yeah. I noticed, if I'm correct, on the different parameters you're looking at, there didn't seem to be anything for chemical oxygen demand or biological oxygen demand. Was there a reason for not having those?
Yeah, because yes, there is a reason, because there is no sensor for those. Those are, those are things where you take water back to the lab and you find out how much oxygen gets used up when you break down the organic matter in it. And it is a variable that is defined by a protocol that takes time to do. Yeah. But the larger issue is we can measure what we have sensors for. And we've been trying to push the boundary on that. As I said, with the Coley minder is new, the nitrous oxide sensor is pretty new. And using CO2 and methane sensors, John and Luke developed a way to do that where they could measure that in water in real time. That was new. But we are limited, we are not sensor developers. So if anyone in this room is, get on it. We need a phosphorus sensor. That's the one we really need. That's been the hard one. Yeah.
Well, I know you can get them for silver and fluorine, among other things.
Yeah. Is there a question back there?
Well, Wisconsin has many inland lakes. The biggest, of course, are Lake Superior and Lake Michigan.
Yes.
How would this type of technology be applied to those big
Yeah, great question. There's a guy at UW Milwaukee who has been doing some things like this. And I know, for example, one thing that I think he has done or one of his colleagues has done is they have put it on not the SS Badger, but the other ferry that goes from Milwaukee to get the transects, which I just thought was brilliant. What a great idea. So the challenge there, of course, is the speed, right? As we said, if it's not fast, it's just lame. And the speed you need to transect Lake Michigan and Lake Superior is substantial. But there's no reason why this technology can't be put on, the Blue Heron or any of these boats on those lakes. And in fact, I have been in touch with a colleague at Ohio State who is writing a proposal right now because she would like to take it on Lake Erie and do whole lake mapping on Lake Erie. And they just have a bigger, faster boat. And so away we go on a bigger, faster boat. All right, 2 more questions? Yep. Yep.
I know this is pertinent to the academic research, which is going to be a foundation for management and so forth. One of the management applications I'm wondering about is for a modified and smaller scale version of this in association with the risk of beach closings. You showed the business, the possibility of E. coli, I guess. And that beach closings are a legitimate management issue in which I can imagine the link in time between this kind of sensor system and the management decisions.
Yep, great question, right? So I think when there are events that happen and the city or county gets very nervous about beaches, they tend to be very active in closing the beaches and then sampling and waiting and cautious. Let's see if I can get back to it. This study here, where we mapped out this coliform activity, was done in collaboration with Kirsty Sorza at the city and county, who is one of the people responsible for making the decision to close the beaches. And the hope is that this sort of being able to detect the enzyme activity basically in real time, that this says, okay, look, you're good here, but man, you just shut these lakes until you know. And this project was spearheaded, as I said, by a colleague from Austria. He has gone back to Austria. So we are on pause for that side of things. But to me, this is exactly where the flame could be really in its sweet spot, to be able to do things like that and get that instant gratification, to really narrow the range to these are the beaches you want to pay attention to. You're good with those beaches. But it's a plan at this point. It's not a process. It's underway. Okay, one more, I guess. Is that right? Or is it coffee time?
What makes a lake turn over and fall?
Yeah, so what makes a lake turn over and fall? That's a great question. It is, so in the summer, you have warm water on top and cool water on the bottom. As you go into the fall and the temperatures get cool, that warm water also cools. And when it gets cool enough that the density difference between the water on top and the water on the bottom is so small that the wind can mix the lake up. It's when the density differences go away because of the cooling of the top layer. Yep.
Can you go into the streaking phenomenon?
What's that?
Can you go into the streaking phenomenon?
Oh, Langmuir spirals. Oh, those are my favorite. Those are that's wind-driven's long cycle. Yeah, no. How's that? That's more complicated. Yes. Yeah. So, all right.